Hello and welcome to Sleepy Scientist. I'm so glad you're here, whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science. Tonight we're going on a deep dive beneath the surface of the Earth. We'll explore the mysterious Earth's crust, that thin, solid outer layer we so often take for granted. It's the surface where we build our homes, travel, and live out our daily lives, but there's so much more to it than meets the eye. Before we begin, take a moment to imagine the Earth, that vast ball spinning in space. Picture the ground beneath your feet, solid, stable, and still. But beneath that is an entirely different world, one that's constantly shifting and changing, slowly molding the surface we live on. In this section, we'll begin to peel back the layers, figuratively, speaking to reveal the hidden wonders of the crust. What do you think lies beneath your feet right now? Are you standing on solid ground, or is there an invisible, ever-moving world below, shaping everything you see? The Earth's crust isn't just a piece of rock. It's a dynamic, shifting structure that plays a crucial role in everything from mountain formation to earthquake activity. So, sit back, relax, and let's take a deep, sleepy journey into the Earth's crust together. Now you might be wondering, what exactly is the crust? In simple terms, the crust is the outermost layer of the Earth. It's the solid shell that surrounds the molten interior of the Earth. Though the crust is thin compared to the layers beneath it, it's still the foundation of everything we experience on the surface. The crust is made up of rocks, minerals, and other materials that form the ground beneath us, and it is divided into two types: the continental crust and the oceanic crust. But don't be fooled by its relative thinness. The crust plays a major role in shaping the landscape and supporting life on Earth. In fact, it's responsible for many of the features that define our planet: mountains, valleys, continents, and even the oceans. Every time you walk on the land, you're stepping on the crust. It's both solid and ever-changing, a thin skin that covers the planet's molten interior. Let's start by talking about the types of crust. The continental crust is thicker and less dense than the oceanic crust. It's composed mostly of lighter rocks, like granite, which gives it a solid, stable appearance. This is the crust that forms the landmasses. We know continents like North America, Africa, and Asia. Continental crust varies in thickness, but on average, it's about 20 to 30 miles thick. This is the crust we're most familiar with, as it supports life, vegetation, and human infrastructure. On the other hand, the oceanic crust is thinner and denser, made mostly of basalt, a dark volcanic rock. The oceanic crust lies beneath the oceans, forming the seafloor. It's much thinner than continental crust, only about 3 to 5 miles thick. Although it's not as visible to us, it plays an equally important role in shaping the Earth. Oceanic crust is constantly being created and destroyed through a process known as subduction, which occurs when one tectonic plate slides beneath another. Now you might be thinking, if both types of crust are made of different materials, what does that mean for the surface of the Earth? How do these two types interact with each other? Well, this is where things start to get really interesting. The Earth's crust is not one solid, unbroken layer. It's made up of large tectonic plates that float on the semi-fluid mantle beneath. These plates are constantly moving, though very slowly, and their movement creates all sorts of fascinating phenomena, from mountain ranges to earthquakes. Have you ever wondered how mountains are formed, or why earthquakes happen? The answers to these questions lie in the way tectonic plates interact. The Earth's crust is divided into several large plates, such as the Pacific Plate, North American Plate, and Eurasian Plate, and they are constantly shifting, sliding, and sometimes colliding with each other. The process that moves these plates is driven by forces deep within the Earth, mostly from convection currents in the mantle. These currents are caused by heat rising from the Earth's core, pushing and pulling the plates on the surface. When these tectonic plates collide, the crust is pushed up to form mountains. One of the most famous examples of this is the Himalayas, which are still growing taller today due to the collision of the Indian plate with the Eurasian plate. This slow but constant movement is what makes the Earth's surface so dynamic. The crust is constantly being reshaped and reformed, but what happens when the plates pull apart? In some areas, the plates move away from each other, creating rift valleys and new ocean floors. A famous example of this process is the Mid-Atlantic Ridge, where the North American plate and the Eurasian plate are moving apart, creating a gap that allows new oceanic crust to form. This is a vital process, as it helps create new land and maintain the Earth's balance. These slow-moving shifts may not seem like much in our day-to-day lives, but they are responsible for major changes over time. Mountains rise, oceans shift, and continents drift. The Earth's crust is in constant motion, and while we may not see it directly, it's shaping the world we live in. So what does all of this tell us about the Earth's crust? It's much more than just the solid ground beneath our feet. It's a dynamic, constantly changing layer full of hidden forces at work. The tectonic plates that make up the crust are constantly moving, colliding, and reshaping the surface of the Earth. And while we experience the effects of these movements through earthquakes, volcanic eruptions, and the formation of mountains, the crust itself is a silent, unseen force that shapes everything we know. But there's more to this story, much more. How does the Earth's crust interact with other layers, like the mantle and the core? What happens when the crust is disturbed, and how do these movements affect the environment? These are questions we'll explore in the next sections. For now, think of the crust as a living, breathing part of our planet, always in motion, always reshaping the world, above and below it. As you continue to relax into the gentle hum of our exploration, imagine this. You're standing in a vast open field. The ground beneath you is solid, unwavering. You can almost feel the pulse of the Earth, but it's hidden quiet beneath the surface. You're safe, but deep below your feet, the Earth's inner layers are stirring and shifting, and this slow, powerful motion is silently shaping the land we walk on. Earlier, we touched on the two types of crust, the continental crust and the oceanic crust, but there's so much more to discover about how these layers are not just static, but incredibly dynamic. We'll now explore the forces that move the Earth's crust and how those forces create the geological activity we witness from time to time. Picture the tectonic plates beneath your feet as enormous, slow-moving puzzle pieces that are constantly in motion. They drift, push, pull, and even collide with each other. What drives this movement? How does the Earth's interior influence what happens on the surface? At the heart of this question lies the idea of plate tectonics, a theory that revolutionized our understanding of how the Earth's crust behaves. This theory explains the movement of the Earth's lithosphere, the rigid outer shell of the Earth, which is broken into large moving plates. The lithosphere rests on a layer called the asthenosphere, which is part of the upper mantle. The asthenosphere is made of semi-molten rock that can flow very slowly over long periods of time. This allows the lithospheric plates to float and move across the surface of the Earth, driven by forces deep within. Imagine the asthenosphere as a thick, slow-moving soup beneath the rigid plates. The heat from the Earth's core causes the rock in the mantle to become buoyant, rising towards the surface, only to cool and sink back down again. This constant up and down motion in the mantle creates convection currents. These currents act like a conveyor belt, moving the tectonic plates along with them. The result, the continents and ocean floors shift, giving rise to dramatic geological features, earthquakes, and volcanic eruptions. If you've ever wondered why the continents are where they are, or why the oceans and mountains have the shape they do, the answer is rooted in this constant, slow-moving process. Take, for instance, the drifting continents. The theory of continental drift, proposed by Alfred Wegener in the early 20th century, suggests that millions of years ago, all of the continents were once joined together in a supercontinent known as Pangaea. Over time, as the tectonic plates moved, the continents began to break apart and drift to their current positions. This movement continues today, though much more slowly, about 1 to 2 centimeters per year. But let's pause for a moment. Have you ever thought about how the Earth's surface is so continuously reshaped by these processes? Why do the continents seem to be drifting apart? And how does the oceanic crust continuously regenerate while the continental crust ages and grows thicker? What keeps these processes in motion? And what effect does this have on the way we experience life on the surface? These are important questions, and they're all tied to the shifting and melting that happens beneath the Earth's crust. When tectonic plates move apart, the crust is pulled apart, creating spaces where new material can be added. This process is most commonly seen at divergent boundaries, like the Mid-Atlantic Ridge. As the plates move away from each other, magma from below the crust rises to fill the gaps. When it cools, it forms new oceanic crust. This continuous creation of new crust is why the Earth doesn't get any bigger over time. It's balanced out by the destruction of older crust at subduction zones, which we'll discuss in a moment. Another fascinating aspect of plate tectonics is how the movement of plates leads to the creation of mountain ranges. When two plates collide, one can be forced beneath the other in a process called subduction, creating what's known as a subduction zone. The plates involved in subduction are both part of the Earth's crust, but they can be very different in nature. For example, the Indian plate, which is made of continental crust, collides with the Eurasian plate, which is also continental, but denser. As the plates collide, the Earth's crust is pushed upwards, forming towering mountain ranges like the Himalayas. This is a slow process happening at a rate of only a few centimeters per year, but over millions of years, it creates massive geological features that can alter the landscape dramatically. And what happens when tectonic plates pull apart? That's when you get the opposite phenomenon, rift valleys and the formation of new ocean floors. These are most noticeable at divergent boundaries where the plates move apart and create space for magma to rise and solidify. A great example of this is the Great Rift Valley in Africa, where the land is slowly splitting apart, causing the formation of a new ocean floor. These rift zones are often hotbeds of volcanic activity as magma rises to fill the gaps. The Earth's crust is thus in a constant state of flux. The surface beneath our feet is not solid or fixed. It's an ever-changing living landscape. It's constantly shaped by the slow but powerful forces of plate tectonics, which move the continents, form mountains, and create oceans. So the next time you look out over a mountain range or stand by the sea, take a moment to imagine what's happening beneath the surface. A world of immense power and energy, invisible to the naked eye, is silently reshaping everything around you. What do you think? How long do you think it takes for the Earth's surface to look the way it does today? Is it truly as stable as it seems? Or is there something more going on beneath the surface, just waiting to emerge? As you settle deeper into your exploration, it's almost as if you can sense the slow, rhythmic movements of the Earth beneath you. The gentle rise and fall of the tectonic plates, the unseen forces shaping the very land you stand on. It's almost like feeling the heartbeat of the planet hidden in the deep, slow churn beneath the surface. We've been talking a lot about tectonic plates and the vast movements that shape continents, But let's zoom in a bit. What happens when these massive plates collide, pull apart, or slide past each other? What exactly happens beneath the surface when they encounter one another? And why does this matter to the ground you walk on? Picture this: two tectonic plates, heavy and ancient, moving in opposite directions. The boundary where they meet is a place of tremendous force and pressure. Depending on the nature of their collision, a range of geological events can unfold, each of them influencing the landscape and life above. These boundaries are where earthquakes and volcanoes often originate, and they serve as the real engines of change beneath your feet. But what's really going on at these boundaries? Let's first take a look at convergent boundaries. This is where two tectonic plates move towards each other. The collision of these plates can create some of the most dramatic geological events in the world. When an oceanic plate meets a continental plate, the denser oceanic plate is forced beneath the continental plate in a process called subduction. This creates deep ocean trenches like the Mariana Trench, the deepest part of the world's oceans. As the oceanic plate is pushed down into the mantle, it melts, and the resulting magma can rise to the surface, forming volcanoes. This is exactly how mountain ranges like the Andes in South America were formed. In this case, the oceanic plate, known as the Nazca Plate, collided with the continental South American plate, forcing it upward over millions of years. The results are towering, jagged peaks that stretch for thousands of miles. But these mountains didn't just appear overnight. They were born from the relentless push and pull of tectonic forces deep within the earth. But it's not just volcanoes and mountains that form at convergent boundaries. The plates involved can also generate earthquakes. When stress builds up at these plate boundaries, it can be released suddenly in the form of seismic waves, what we experience as an earthquake. This is the Earth's way of releasing pressure, a process that can be both violent and unpredictable. The energy released during an earthquake can cause the ground to shift and even crack open, affecting everything on the surface. Some of the most powerful earthquakes in history have been linked to these convergent plate boundaries where tectonic stress is at its peak. Now, what about divergent boundaries where plates move away from each other? In these areas, we often find rift valleys and mid-ocean ridges, such as the famous Mid-Atlantic Ridge. Here, the plates are pulling apart, and magma from the mantle rises up to fill the gaps, forming new crust as it cools. This process is responsible for the creation of new ocean floor. In fact, the Mid-Atlantic Ridge is the longest mountain range in the world, stretching over 40,000 miles beneath the ocean's surface. It's also the site of continuous volcanic activity, as magma is constantly being pushed up from the mantle. But the action isn't limited to oceans. Rift valleys like the East African Rift are places where continents themselves are being slowly torn apart. Here, the Earth's crust is being stretched and cracked, and over millions of years, it could eventually split into two separate landmasses. The East African Rift is particularly intriguing because it's an active rift, and scientists have even observed the formation of small volcanic islands as a result of this tectonic activity. Imagine the slow, deliberate act of a giant continent stretching at a pace so slow it's nearly imperceptible, yet over time it leads to the birth of new landforms. Lastly, let's consider the transform boundaries, where tectonic plates slide past each other. This kind of movement isn't about pushing or pulling, but about plates grinding against each other horizontally. While it may sound like an eerie, subtle shift, this type of movement can also be quite dramatic. As the plates move, they sometimes get stuck due to friction. When the stress finally overcomes the friction, it releases in the form of an earthquake. The San Andreas Fault in California is one of the most famous examples of this kind of boundary, where the Pacific Plate slides past the North American Plate. It's a constant reminder that even when the movement isn't vertical or horizontal, the tension can still result in sudden dramatic shifts. These three types of boundaries, convergent, divergent, and transform, are not just places where tectonic plates meet. They are where the Earth's energy is released and transformed. The processes happening at these boundaries don't just shape mountains, valleys, and ocean ridges. They also directly affect the stability of the surface and can cause life-altering events like earthquakes and volcanic eruptions. They're a reminder that beneath our feet, the Earth is constantly at work, sculpting the landscape in ways that we're often unaware of until a tremor shakes the ground beneath us. Have you ever thought about how we live on top of such an active, powerful system? Imagine standing on a shifting tectonic plate, moving ever so slightly with time. How do you think the forces deep inside the Earth compare to the forces on the surface? Does this new understanding of the Earth's active nature shift the way you think about the ground we stand on? As the ground shifts beneath you, the deeper you dig into the Earth, the more you realize it's not just the tectonic plates that make the planet feel alive. The very layers beneath your feet hold a multitude of secrets, and the deeper you go, the more wondrous and sometimes unsettling it becomes. You've already learned that the Earth's crust is the thin outer shell that we stand on, but what lies beneath it is where the true story of our planet begins. To get a sense of the immense pressures and forces at play, imagine this. You're standing on the outermost layer of an onion, and you've only just started peeling back the skin. What lies beneath that skin, buried in the Earth's interior, is where the real action happens. You see, the Earth has multiple layers, each with its own characteristics and behavior, influencing everything from volcanic eruptions to the formation of mountains. Let's begin by taking a deeper dive, starting with the mantle, the thick, semi-solid layer beneath the crust. It's not like the crust at all. It's far more dense and much thicker. Stretching nearly 1,800 miles beneath the surface, it's made of silicate rocks, rich in magnesium and iron, and while it might seem solid, it's actually quite fluid, just not in the way we think of liquids. The mantle behaves like a slow-moving plastic-like substance, with material that can take hundreds of millions of years to move from one place to another. That's right, the mantle is in constant motion, but at a pace so slow it's imperceptible to the human eye. It's here in the mantle that convection currents come into play. These currents are essentially giant, slow-moving loops of molten rock rising and sinking due to heat from the core. It's these convection currents that play a massive role in shaping the Earth's surface. As hot material from the lower mantle rises, it pushes against the overlying crust, forcing it to move and creating the shifting of tectonic plates. Imagine the molten rock rising through a thick liquid and pushing against everything in its path. Over long periods of time, this movement can lead to the formation of mountain ranges, the sinking of ocean basins, and even the tearing apart of continents. It's a slow, relentless process, but one that has been going on for billions of years and will continue as long as the planet exists. So if the mantle is constantly moving, where does that leave us with the outer core? The outer core lies beneath the mantle, about 1,800 miles beneath the Earth's surface. Unlike the mantle, which is made of solid rock, the outer core is liquid, mostly composed of molten iron and nickel. Imagine the heat from the Earth's core reaching temperatures of around $9,000 to 13,000 degrees Fahrenheit, causing the metals within this layer to melt, creating a thick, churning ocean of liquid metal. But here's where things get interesting. The movement of the molten metal in the outer core is what creates the Earth's magnetic field. As the liquid iron moves and churns, it generates electric currents, and these currents in turn create magnetic fields. If you've ever wondered how we have a magnetic field to protect us from harmful solar radiation, it's all thanks to the dynamic processes happening in the outer core. Without this magnetic field, life on Earth would be exposed to harmful cosmic rays and solar wind. So in a way, this turbulent molten layer of liquid metal is one of the key reasons why life exists as we know it. But don't get too comfortable yet. The real heart of the Earth lies beneath the outer core, the inner core. The inner core is composed of solid iron and nickel, and despite the immense heat around it, it remains solid because of the tremendous pressure it's under. It's like a dense ball of iron, radiating an extraordinary amount of heat, yet remaining tightly compressed in its solid form. The temperature here is comparable to the surface of the sun, reaching around 13,000 degrees Fahrenheit, yet the pressure is so high that the iron remains solid. And although it may seem like a featureless, inaccessible region, the inner core actually plays a crucial role in our planet's function. Its rotation combined with the movement of the outer core creates a dynamo effect which sustains the Earth's magnetic field. This dynamo effect is the reason we have a compass that points north, the reason birds migrate using Earth's magnetic fields, and the reason we have the aurora borealis as charged particles interact with the magnetic field near the poles. Without this system, Earth would be a very different place. At this point, you might be wondering, why are we so fascinated by the layers beneath our feet? Well, the simple truth is that understanding the Earth's interior not only helps us grasp how our planet has evolved over billions of years, but also helps us better predict natural disasters like earthquakes and volcanic eruptions. By studying the material composition movement and behavior of the Earth's layers, we gain insight into how and why the Earth changes over time. It's like being given a map to the inner workings of the planet, allowing us to predict certain geological events, and in some cases, even protect ourselves from them. So as you stand perhaps with your feet resting on the Earth, consider the immense unseen forces beneath you, slowly shaping and reshaping the land, crafting the very environment you live in. How might this deep inner world continue to surprise us in the future? Will we ever fully understand the depth of the planet's core? What if there are even more forces at play than we realize? As you stand on the surface of the Earth, surrounded by the familiar landscape of land, sea, and sky, it's easy to forget the profound forces that are constantly at work beneath your feet. But if you pause and listen closely, you might just hear the faint rumblings of something more, something deep within the Earth's layers, waiting to make its presence known. These rumblings are the product of the tectonic plates, massive sections of the Earth's crust that are constantly moving, grinding, and reshaping the planet's surface. The idea that the Earth's surface is a patchwork of large shifting pieces is relatively new. Only in the 20th century did scientists begin to piece together the theory of plate tectonics. Imagine a jigsaw puzzle, but instead of static pieces, these pieces are constantly moving and shifting, drifting on the mantle beneath them, like massive icebergs floating on a sea of molten rock. The plates vary in size, with some spanning entire continents and others covering vast stretches of ocean. And while these plates may seem massive, they move incredibly slowly, sometimes only a few centimeters per year. Despite their slow pace, the impacts of their movements are felt on a global scale, influencing everything from earthquakes to the formation of mountain ranges. But how do these plates actually move? The driving force behind their motion lies deep within the mantle, where the heat from the core creates convection currents, slow-moving currents of hot material rising and cooler material sinking. This movement within the mantle generates enough force to push the tectonic plates around like giant conveyor belts beneath the Earth's surface. As the plates move, they interact with each other in different ways, leading to different types of plate boundaries and phenomena. The first type of boundary is the divergent boundary, where two plates move away from each other. This often occurs along mid-ocean ridges, where new oceanic crust is created as magma from the mantle rises to fill the gap. As the magma cools and solidifies, it forms new crust, pushing the existing crust apart. Imagine this like a zipper slowly being undone with new material constantly filling the gap between the separating plates. The Mid-Atlantic Ridge is one of the most well-known examples of a divergent boundary where the Eurasian and North American plates are slowly drifting apart, creating new oceanic crust beneath the Atlantic Ocean. On the other hand, you have convergent boundaries where two plates move toward each other. This is where the action really heats up literally. When two tectonic plates collide, one plate may be forced beneath the other in a process known as subduction. Subduction zones, such as the boundary between the Pacific and North American plates, create some of the most dramatic geological events on the planet. As the subducting plate is forced into the mantle, it melts and causes magma to rise, which can lead to the formation of volcanoes. The Ring of Fire, a horseshoe-shaped belt around the Pacific Ocean, is home to many of the world's most active volcanoes and is a direct result of subduction zones along convergent boundaries. But it's not just volcanic activity that occurs at these boundaries. The collision of two plates can also lead to the formation of mountain ranges. Take the mighty Himalayas, for example. The Indian plate is slowly colliding with the Eurasian plate, and as the two plates push against each other, they form the towering peaks of the Himalayas, the highest mountain range on Earth. Over millions of years, the plates continue to press against one another, pushing the mountains higher and higher. It's a slow but relentless process, one that has been ongoing for millions of years and will continue for millions more. Then there are transform boundaries where two plates slide past each other horizontally. These boundaries are marked by faults fractures in the Earth's crust, where the plates grind against each other. One of the most famous transform boundaries is the San Andreas Fault in California. This fault is responsible for some of the most significant earthquakes in the region, as the Pacific Plate and the North American Plate slide past each other. The grinding motion between the plates can create intense pressure, and when that pressure is released, it results in an earthquake. It's a reminder that beneath the calm, stable appearance of the Earth's surface, the plates are always in motion, and sometimes that motion can be quite dramatic. As you think about all these different types of boundaries and their associated phenomena, it's hard not to be amazed by the sheer power of the forces at play. The Earth is constantly evolving, and its surface is never truly static. The next time you feel a tremor beneath your feet, or notice the quiet rise and fall of the landscape around you, remember that these movements are part of a vast and complex system that shapes the planet over time. But you might be wondering, how do scientists study these massive, often invisible forces? After all, we can't just send a camera crew into the deep Earth to capture footage of the mantle or the core. The answer lies in the study of seismic waves, or the vibrations that travel through the Earth when there's an earthquake or other geological event. By studying how these seismic waves travel through the Earth's layers, scientists can map out the structure and composition of the Earth's interior. It's like using a form of sonar, where waves are sent through the Earth, and their reflections provide us with a picture of what's below. It's through these seismic waves that we've learned so much about the Earth's layers, the crust, the mantle, the outer core, and the inner core. In a sense, the Earth's interior is speaking to us all the time, and seismic waves are the whispers of the planet, carrying with them the stories of its past, present, and future. And as we continue to study the shifting of tectonic plates and the forces that drive them, we come closer to understanding the vast, dynamic system that lies beneath our feet. The question remains, what will we discover next? How will our understanding of the Earth's crust and interior evolve over time? And as we uncover more of these secrets, how might we harness that knowledge to protect ourselves from the natural forces at play beneath our feet? The Earth's story is far from over, and we're only just beginning to scratch the surface. Easy to forget its immense power. It's a place where pressure and heat collide in a slow, steady dance, shaping the landscape above us in ways we rarely see. You might find yourself wondering, what exactly is going on down there? What forces are at work beneath your feet, far beyond the shallow surface where we live? The answer lies in the mantle, a vast layer of the Earth that stretches from beneath the crust all the way to the outer core. To understand the mantle, imagine a loaf of bread where the crust is the outer layer, and the inside is soft and squishy, but also dense and powerful. The mantle makes up the bulk of the Earth's volume, and though it's solid, it's far from still. It behaves in a way that's not entirely solid, not entirely liquid. It's something in between. This strange semi-solid state is due to the intense heat and pressure that make parts of the mantle behave like a thick, slow-moving liquid, while other parts remain more solid. This unusual behavior allows the mantle to flow in a process called mantle convection, which drives the movement of tectonic plates above it. If you've ever seen a lava lamp, you've witnessed a miniature version of mantle convection at work. The lamp heat causes the wax to rise cool and sink back down again. On a much larger scale in the mantle, the hotter, less dense material rises, and as it cools, it sinks. This cycle creates a constant motion of material, like a stirring pot of molten rock deep inside the Earth. The Earth's mantle extends about 2,900 kilometers, 1,800 miles down into the planet. That's more than half of the Earth's radius. The uppermost part of the mantle is the asthenosphere, a layer that's more fluid-like and capable of flowing over long periods of time. Above this, we have the lithosphere, the solid outermost layer, which is where the tectonic plates rest. It's the slow, continuous movement of the mantle that powers plate tectonics, driving the formation of mountains, earthquakes, volcanoes, and more. It's almost like the mantle is constantly stirring the Earth's surface, setting the stage for the dynamic changes we see. But the mantle isn't just a giant mixing pot of molten rock. It's also an important source of heat. The heat within the mantle comes from two sources: the leftover heat from the planet's formation, and the heat produced by the decay of radioactive elements such as uranium and thorium. This heat is what keeps the mantle in motion, and by extension, keeps the tectonic plates shifting. Without this heat, the Earth would be a very different place. The motion of the plates driven by mantle convection is what helps sustain life as we know it. It's the reason we have continents that drift and collide, forming new landmasses and shaping our environment. Yet even as we begin to understand the basic principles of mantle convection and the flow of heat, there's still so much about this hidden world we don't fully grasp. For example, why do some areas of the mantle appear to move faster than others? What causes the irregularities in mantle flow that result in the formation of hot spots where volcanic activity occurs far from plate boundaries? Think of the Hawaiian Islands, a chain of volcanic islands in the middle of the Pacific Ocean, far from any tectonic plate boundary. These islands were formed by a hot spot beneath the Pacific Plate, where a plume of hot mantle material rises from deep within the Earth and melts the crust, forming volcanoes. Hot spots are like mysterious pockets of heat in the mantle, and they raise interesting questions about how the Earth's interior works. The mantle also holds clues about the history of our planet. By studying the way heat moves through the mantle, scientists can learn about the Earth's early days, about how the planet formed, how it evolved, and how its internal structure has changed over billions of years. For instance, scientists have discovered that the mantle is not uniform throughout. It has regions of varying temperature and composition. Some parts of the mantle are hotter and more fluid, while others are cooler and denser. These variations help shape the behavior of the plates above and provide important clues about the planet's geological history. As you contemplate this strange, slow-moving, and mysterious realm, you may find yourself wondering, how far have we really explored? Despite the fact that the mantle holds so many secrets, we've only scratched the surface. While we can observe the mantle's effects through seismic waves and volcanic activity, we've never been able to directly study the mantle itself. After all, the pressure and heat are so extreme that it's impossible for us to send a probe to the depths of the mantle yet. But we're getting closer. Technology is advancing, and with new methods like seismic tomography, essentially using seismic waves as a form of X-ray to study the mantle, we are beginning to map out the deep, unseen layers of the Earth. We might never be able to directly see the mantle in the way we can study the surface, but with each new breakthrough, we uncover a little more of its mystery. So the next time you find yourself standing on solid ground, remember that beneath your feet, a dynamic, ever-moving system of heat and pressure is at work. The mantle may be hidden from view, but its influence shapes the world around you in ways that are both subtle and profound. The Earth's crust, the tectonic plates, the volcanoes, the mountains, they are all part of a grand interconnected dance that takes place deep beneath the surface, driven by the slow, steady churn of the mantle. It's a reminder that even the most familiar parts of our planet are shaped by forces we can't always see, but can certainly feel. Let's drift deeper into the Earth's interior and explore the next layer, the outer core. The mantle may be vast and ever-changing, but the outer core represents a radically different part of our planet's makeup. In fact, the outer core is one of the most fascinating and mysterious regions beneath our feet. It's here about 2,900 kilometers, 1,800 miles below the Earth's surface, where the planet starts to truly change its character. If you thought the mantle was dramatic, just wait until you hear about the fiery cauldron beneath it. Imagine being swallowed by a world so hot that nothing, not even rocks, can remain solid. The outer core is primarily made of liquid iron and nickel metals so hot that they've melted into a molten state. Temperatures here range between 4,000 and 6,000 degrees Celsius, 7,200 to 10,800 degrees Fahrenheit, which is nearly as hot as the surface of the sun. Can you feel the heat? It's a place where the pressure is so intense that the iron and nickel are forced into a liquid form, despite their usual solid state at surface temperatures. This molten metal is not just a random sea of liquid. The outer core plays a crucial role in generating the Earth's magnetic field, something we take for granted, but it's essential for life on Earth. This magnetic field acts like a shield, protecting the planet from harmful solar radiation and cosmic rays. Without it, the Earth's atmosphere could have been stripped away by the sun's solar wind, leaving the planet vulnerable to harsh conditions. How does the outer core create this magnetic field? The answer lies in the motion of the molten metals within the core. As the liquid iron and nickel move, they generate electric currents. These currents create magnetic fields, and when combined with the rotation of the Earth, they produce a geodynamo, a self-sustaining mechanism that generates the magnetic field. It's like the Earth has its own internal engine that keeps the magnetic field alive and humming. This process is complex, and scientists are still working to fully understand all the factors involved. If you've ever wondered why compasses point north, or why the aurora borealis dances across the night skies, in the polar regions you can thank the outer core. The magnetic field created by the outer core interacts with charged particles from the sun, creating the stunning displays of the northern and southern lights. These dazzling colors are the result of the charged particles being funneled by the magnetic field toward the poles, where they collide with the atmosphere, producing bursts of light. It's worth noting that the outer core isn't static, it's dynamic, constantly in motion. The liquid iron and nickel move and churn, creating convection currents that drive the motion of the molten metal. Just as the mantle below it moves in a slow but persistent churn, the outer core does the same with its molten metals constantly circulating. This movement is a critical part of how the Earth's magnetic field is generated and sustained. You might be curious about one thing: if the outer core is a vast ocean of molten metal, why don't we see volcanoes or other signs of activity directly related to it? The answer lies in the fact that the outer core is enclosed within the solid mantle. While the mantle is full of dynamic movement, it keeps the molten material of the outer core protected and out of view. However, the effects of the outer core's activity are felt all over the planet, even if we can't see it. The magnetic field it creates affects our electronics compasses and even the health of our satellites orbiting the Earth. Despite all that we know, there's still much to learn about the outer core. While we can study the magnetic field generated by the core, we cannot directly access it. Our understanding of this layer relies largely on indirect measurements, such as the behavior of seismic waves traveling through the Earth. These waves can pass through different materials at different speeds, which gives us clues about the structure and state of the outer core. Interestingly, seismic waves travel more slowly through the outer core than through the solid mantle, indicating that the outer core is indeed liquid. One of the most compelling mysteries surrounding the outer core is whether or not it's in a state of constant change. The outer core is thought to be slowly cooling over time. As it cools, the molten iron and nickel crystallize, possibly forming solid layers at the core's boundary with the mantle. This slow cooling process might be a factor in the gradual weakening of the Earth's magnetic field, a phenomenon that's been observed in some regions over the last few hundred years. However, the Earth's magnetic field is also highly dynamic, with the poles flipping positions every few 100,000 years or so. Scientists are still studying the reasons behind these magnetic reversals and their connection to the core's activity. This idea of the outer core slowly cooling down also brings up an interesting question. If the core is cooling, what happens to the material that crystallizes at the boundary? Does it sink back down into the mantle, or does it somehow affect the surrounding material? We're still uncertain about these details, but they're crucial for understanding the long-term evolution of the Earth's core. You might also wonder how this dynamic molten core affects the Earth's overall behavior. For instance, we've talked about the magnetic field, but how does the inner core, the solid center of the Earth, fit into this picture? What happens at the boundary between the liquid outer core and the solid inner core? These questions, though unanswered, help drive scientific curiosity and fuel research into the deepest parts of our planet. As you let all this sink in, think about the power of the outer core. It's not just a molten mass of metal beneath us. It's a vital force that shields our planet, influences our technology, and shapes the atmosphere around us. It's one of the unseen forces that make Earth such a unique and habitable planet in the vast cosmos. And though we may never journey to the depths of the outer core ourselves, we can continue to explore and marvel at the incredible processes that happen beneath our feet. Now that we've ventured into the molten heart of the Earth's outer core, it's time to make our way even deeper, past the swirling rivers of liquid iron, into the most mysterious and solid part of our planet, the inner core. This is where the story of Earth's structure takes a fascinating twist. Imagine yourself drifting even further below the surface, where the temperatures are unimaginable and the pressure is beyond anything we can experience on the surface. It's a place so alien that the conditions are nearly impossible to recreate in a laboratory. But still, scientists are piecing together what we can about the inner core, one small clue at a time. The inner core is, in simple terms, a giant solid ball of iron and nickel, with a radius of about 220 kilometers, about 760 miles. At first glance, that might not seem like much compared to the vast size of the Earth, but when you consider the fact that it's under extreme heat and pressure, it's an impressive feature. Temperatures here hover around 5,500 degrees Celsius, 9,900 degrees Fahrenheit. That's nearly as hot as the surface of the sun. Despite the intense heat, the inner core remains solid. This is because the pressure at such depths is so immense that the iron and nickel, normally in a liquid state at lower pressures, are compressed into a solid form. It's hard to imagine how something can remain solid under such extreme temperatures. The key lies in the enormous pressure at these depths. As you move deeper into the Earth, the weight of the layers above you becomes heavier and heavier, pressing everything down. This pressure is so intense that it actually forces the iron and nickel atoms to stay packed closely together despite the heat. In fact, the pressure at the Earth's center is about 3.6 million times greater than the pressure at sea level. That's a lot of weight resting on top of the inner core, but it's also what makes it solid. But why is the inner core so important to understanding the Earth's overall behavior? Well, it's the center of everything, the very heart of our planet. The inner core may be surrounded by the hot fluid outer core, but it plays a key role in the generation of the Earth's magnetic field. Although the outer core is the main contributor to the magnetic field, the inner core also has an influence. The solid inner core rotates at a slightly different speed than the rest of the planet, a phenomenon known as differential rotation. This slight difference in speed may contribute to the dynamics of the geodynamo, the process that generates the Earth's magnetic field. Here's something else that may surprise you. Despite the inner core's solid nature, it's not as simple as a uniform ball of metal. The inner core is thought to be made up of several layers, with the outermost layer being a bit softer than the rest. Scientists have found that the inner core might not be a single solid mass, but rather a layered structure, with the innermost part possibly made up of pure iron. This discovery came from studying the way seismic waves travel through the Earth. Seismic waves move through different materials at different speeds, and by measuring how they travel through the Earth, scientists can get clues about the internal structure. There's still much we don't know about the inner core. For instance, we don't yet fully understand the exact composition of this mysterious region. Some scientists believe that lighter elements such as sulfur or oxygen might be mixed in with the iron and nickel. These elements could have been incorporated into the inner core as the Earth formed, or they could have migrated there over time. The presence of these lighter elements would explain some of the unusual properties of the inner core, such as its lower density compared to pure iron. The idea of a liquid outer core and a solid inner core might sound like an odd pairing, but they work together to create a planet with extraordinary characteristics. The interplay between the inner and outer core creates a kind of balance within the Earth's structure. The inner core remains solid due to immense pressure, while the outer core's liquid state provides the dynamo effect that powers our magnetic field. Have you ever wondered how Earth's core might change over time? Just as the outer core is slowly cooling, the inner core is also evolving. One of the most intriguing questions in geology is how the inner core might have formed. Some scientists suggest that the inner core began forming shortly after the Earth's formation, about 4.5 billion years ago. As the Earth cooled, the solid iron and nickel began to crystallize at the center, while lighter materials like sulfur and oxygen migrated outward. The formation of the inner core has likely been a gradual process. Over time, the inner core has grown by solidifying material from the outer core. This slow growth is probably responsible for the changing magnetic field that Earth experiences. If you've ever heard about the geomagnetic reversals, the flipping of the magnetic poles, This process might be influenced by the changes in the inner core, although the details are still a bit unclear. Another fascinating aspect of the inner core is the heat transfer that happens between the inner core and the outer core. As the inner core solidifies, it releases heat into the surrounding outer core. This heat plays a role in the convection currents within the outer core, which in turn help generate the Earth's magnetic field. Essentially, the inner core is not just a passive solid mass. It's an active player in the planet's dynamic processes. The idea that the inner core is slowly growing while the outer core cools might seem like a subtle, gradual process, but it has far-reaching implications. As the Earth's internal heat begins to dissipate, the planet's overall dynamics will change. For instance, the magnetic field could weaken, and the rate at which tectonic plates move could be affected. These long-term changes will help shape the Earth as we know it, though it will take millions or even billions of years to fully see the results. As you settle deeper into the Earth's layers, think about the inner core as the last piece of the puzzle, the solid anchor at the very center of our planet. While we may never be able to visit this remote part of Earth, its presence affects everything from the magnetic field to the stability of our planet. It's one of the great mysteries of our world, hidden deep within, yet essential to the very nature of the planet beneath your feet. Now that we've reached the very core of the Earth, it's time to travel back up through the layers, taking a closer look at what surrounds the inner core. The outer core, a vast and dynamic liquid ocean of molten metal. Just like the inner core, the outer core is made primarily of iron and nickel, but it has a very different nature. The temperature here is incredibly hot, around 4,000 to 5,000 degrees Celsius, 7,200 to 9,000 degrees Fahrenheit. But unlike the inner core, the outer core remains in a liquid state due to lower pressure. Imagine the outer core as a roiling, turbulent sea of liquid metal constantly in motion beneath the Earth's solid crust. The outer core plays a crucial role in the Earth's geodynamics, helping to drive the convective currents that generate our planet's magnetic field. You may have heard of the geodynamo. This process is essentially the engine that powers Earth's magnetic field. It's a result of the convective movement of molten iron and nickel within the outer core, combined with the Earth's rotation. These materials move in large convection currents, where hot material rises from the inner core to the outer core and then cools as it moves towards the mantle. This continuous flow of molten metal generates electric currents, and the movement of these currents in turn creates a magnetic field. The Earth's magnetic field extends far out into space, protecting us from harmful solar radiation and even helping animals navigate. But what exactly drives these convection currents? Well, as you might expect, it's the combination of heat and pressure within the outer core. The heat emanates from the inner core, but it doesn't just stay there. It pushes its way outward, heating up the surrounding material in the outer core. As the molten metal rises toward the mantle, it cools, and then it sinks back down toward the inner core, creating a cycle of motion that over time fuels the geodynamo. It's this continuous energetic process that powers our magnetic field, one of Earth's most crucial protective mechanisms. The convective currents also have an indirect but significant effect on the Earth's surface. You see, the outer core's movement is intimately linked with the motions of the Earth's tectonic plates. While the convection currents themselves don't directly move the plates, they help drive the heat and flow within the mantle, which in turn influences the movement of the plates above. It's a delicate dance. The heat and flow from the outer core affect how the mantle behaves, which then impacts the surface. Have you ever wondered why the Earth has such a strong magnetic field compared to other planets in our solar system? It's all thanks to this molten outer core and the dynamic process that takes place beneath our feet. Mars, for example, doesn't have a global magnetic field, which has led scientists to believe that its core might have cooled and solidified long ago. The Earth's outer core, still full of molten metal, keeps churning and creating a magnetic field that shields us from the harsh solar winds and cosmic radiation. It's like an invisible shield helping to preserve life on Earth, and it all happens deep below the surface, in the heart of the planet. But despite its importance, the outer core remains one of the most difficult parts of Earth to study. Why? Because it's hidden beneath miles of solid rock, making it nearly impossible for us to directly observe. We can't just dig a hole to the center of the Earth and take a peek. Instead, scientists rely on seismic waves, the shock waves created by earthquakes, to study the outer core's behavior. Seismic waves travel through the Earth, and by analyzing how these waves behave when they encounter different materials, scientists can infer the properties of the materials they pass through. For example, seismic waves travel much more slowly through liquids than they do through solids. When researchers measure the speed and path of seismic waves, they can tell when they're moving through the solid mantle, the liquid outer core, and the solid inner core. It's like having a sonar map of the planet, but one that's been created through the shaking of the Earth itself. One of the most intriguing mysteries about the outer core involves its composition. While scientists know it's mostly made of molten iron and nickel, there's still debate over the exact mix of elements. There are hints that lighter elements, such as sulfur oxygen and silicon, might be mixed into the molten metal, though their exact roles are still a subject of ongoing research. Why does this matter? Well, understanding the composition of the outer core is essential for understanding how the Earth's magnetic field is generated. These elements could also influence the thermal properties of the core and how the heat is transferred from the inner core to the mantle. It's a piece of the puzzle that could shed light on the complex workings of the Earth's interior. The outer core is also responsible for another fascinating phenomenon: earthquakes. When the energy from an earthquake travels through the Earth, it passes through both solid and liquid regions. By studying how seismic waves move through the outer core, scientists can learn more about how the Earth behaves under stress. The way seismic waves travel through different layers of the Earth has been key to understanding not just the outer core, but the entire internal structure of our planet. So in a sense, the outer core is both a powerful engine and a window into understanding the forces that shape the Earth. It's constantly in motion, churning and flowing, creating the magnetic field that protects us and influencing the mantle's movements, which ultimately affect the Earth's surface. Though we can't see it with our eyes or touch it with our hands, the outer core is always there, silently driving the forces that make our planet the unique and dynamic world it is. Now take a moment to imagine yourself standing on the Earth's surface, with the knowledge that beneath your feet there are powerful swirling currents of molten metal. These currents, invisible to us, are quietly keeping our planet alive and dynamic, shaping everything from the magnetic field that protects us from the cosmos to the tectonic plates that carve out our mountains and oceans. It's as if the Earth itself is a living, breathing organism, constantly shifting and evolving. As we move upwards from the outer core, we enter the mantle, the vast, mostly solid layer that makes up the majority of the Earth's volume. Think of it as the planet's engine room, a place where immense heat and pressure cause materials to flow and shift slowly over millions of years. While the mantle is solid, it behaves a bit like a thick, slow-moving fluid. It's here that we begin to witness the incredible tectonic processes that shape the surface of our world. Volcanoes erupt, continents drift, and mountain ranges form. But before we get into the action of these processes, let's take a moment to dive deeper into what the mantle is made of and how it behaves. The mantle is primarily composed of silicate minerals with a blend of iron and magnesium, giving it a denser, heavier makeup than the crust above. It's divided into two main regions, the upper mantle and the lower mantle. The upper mantle extends to about 410 kilometers, 255 miles below the Earth's surface, and is where the most significant tectonic movements happen. It's here that the Earth's lithosphere, the rigid outer shell, rests on top of the semi-fluid asthenosphere, a portion of the upper mantle that behaves plastically due to the high temperatures. This interaction between the lithosphere and the asthenosphere is what allows the tectonic plates to move, albeit very slowly, on the order of a few centimeters per year. So while you're relaxing, the Earth's plates are sliding and shifting beneath you, but at a pace so slow you wouldn't notice unless you look at it over the course of millions of years. This movement might sound harmless, but it's actually what drives many of the most dramatic natural events on Earth, like earthquakes, volcanic eruptions, and mountain formation. The energy created from the movement of tectonic plates in the mantle results in plate tectonics, which causes the Earth's crust to break apart and form new land. Imagine the plates of the lithosphere like giant puzzle pieces that are slowly sliding around on a smooth yet sticky layer of molten rock. Every time two plates collide, one might be pushed under the other in a process called subduction. This is what leads to the formation of deep ocean trenches like the Mariana Trench, the deepest part of the world's oceans, or volcanic arcs such as the famous Ring of Fire, a volcanic belt that circles the Pacific Ocean. But this interaction between the crust and the mantle isn't just about destructive forces, it's also about creation. Over time, the slow movement of the tectonic plates leads to the formation of new land and the shaping of the world as we know it. Have you ever wondered why some parts of the Earth are constantly rising while others are sinking? It's because of the ongoing processes of plate tectonics, where the mantle's material moves to the surface and forms new mountains and ocean basins. For example, the Himalayas, the tallest mountain range on Earth, are still rising today as the Indian plate pushes against the Eurasian plate. At the same time, the mantle isn't entirely uniform. It contains areas of hotspots, places where hotter than normal material from deep within the Earth rises to the surface. These hotspots are thought to be relatively stationary, meaning that as the tectonic plates move over them, they can create chains of volcanic islands like the Hawaiian Islands. The volcanoes here are fed by mantle plumes, rising columns of hot rock from deep within the Earth that create volcanoes as they reach the surface. These plumes don't follow the movement of the tectonic plates, so as a plate moves over a hotspot, the volcanoes in that area are no longer active. This process leaves behind a trail of islands, each progressively older, as you move away from the current location of the hotspot. One fascinating aspect of the mantle is how it behaves under pressure. As you descend deeper into the Earth, the temperature and pressure increase significantly, causing the minerals in the mantle to undergo phase changes. At certain depths, the materials shift from one crystalline structure to another. For instance, minerals such as olivine and pyroxene undergo transformations as they are subjected to extreme heat and pressure. These phase changes contribute to the mantle convection process, where hotter material rises and cooler material sinks. This convection is what keeps the mantle in constant motion and is responsible for much of the tectonic activity we observe on Earth. Have you ever wondered why the Earth doesn't just stay static? It's the mantle's slow but relentless flow that constantly reshapes the planet. While humans may think of the Earth's surface as a permanent fixture, the reality is that its surface is in a constant state of flux. Volcanoes and earthquakes are the visible signs of the dynamic processes occurring deep beneath the surface. Without these processes, our planet would be much different, perhaps even less habitable, as the continuous movement of tectonic plates helps regulate the Earth's temperature and allows for the cycling of essential elements like carbon. The Earth's surface is constantly being recycled by the mantle, renewing itself over geological timescales. The study of the mantle is one of the most important areas of geology because it helps scientists understand the processes that shape not only the Earth's surface, but also its internal dynamics. Thanks to tools like seismic tomography, which uses seismic waves to create 3D images of the Earth's interior, scientists can now see deeper into the mantle than ever before. This technique has revealed mantle plumes and even superplumes, gigantic upwellings of hot mantle material that may be responsible for some of the planet's most profound geological events, such as the formation of continents and supercontinents. It's quite mind-boggling to think that all of these processes, subduction, convection, volcanic activity, are happening beneath our feet, all the while shaping our world in ways that we often don't even realize. And yet, despite all the chaos of the mantle's movement, the surface of the Earth remains mostly stable in our day-to-day experience. It's almost as if the Earth is slowly and patiently knitting itself together, as a quiet reminder that while the world may seem calm on the surface, there's always something extraordinary happening deep beneath. So next time you stand on solid ground, consider how the mantle is busy at work far below. All those quiet movements are transforming the world, creating mountains, forming valleys, and shifting continents. It's the ultimate reminder that even in the moments of stillness, the Earth is constantly alive and changing slowly but surely right beneath our feet. As we sink deeper into the Earth's interior beyond the mantle, we reach the outer core. This region with its liquid state is unlike anything we've yet encountered on our journey. Imagine an immense sea of molten metal that stretches for nearly 2,300 kilometers, 400 miles beneath your feet. The outer core is made mostly of iron and nickel, and it plays an essential role in the Earth's magnetic field, a feature so crucial that without it, our world would be a much harsher place to live. The outer core's existence remains a bit mysterious, but scientists have pieced together much of its nature, and it is a key component of the planetary engine that drives Earth's dynamic systems. The outer core's liquid state is a result of the extreme temperatures present so far beneath the Earth's surface. Temperatures here range from 4,000 to 6,000 degrees Celsius, 7 to 32 to 10,832 degrees Fahrenheit, which is far hotter than the surface of the sun. However, the reason the outer core is liquid rather than solid is because the pressure is much lower than it is in the inner core, which we will explore shortly. The lower pressure allows the metals in the outer core to melt and flow, creating an ever-moving, ever-churning mass of molten iron and nickel. These materials flow and move in complex currents which generate the Earth's magnetic field through a process called the geodynamo. The geodynamo is an amazing mechanism, as the liquid metals of the outer core move, their motions generate electrical currents, which in turn generate magnetic fields. These fields then interact with each other, creating a dynamic, self-sustaining system. Think of the Earth's magnetic field as a giant protective shield, one that extends far beyond the surface, out into space. This magnetic field is critical because it protects the planet from harmful solar radiation and cosmic rays, deflecting much of this high-energy radiation away from our atmosphere and keeping it safe for life. Without it, the Earth's atmosphere would slowly be stripped away, and conditions on the planet would become much more hostile to life. The magnetosphere, the area of space influenced by the Earth's magnetic field, is also what causes the beautiful auroras, or northern and southern lights, to form when charged particles from the sun collide with the Earth's atmosphere. Have you ever thought about the magnetic forces you feel around you every day? Every time you interact with a magnet, you're connecting to the very core of the Earth. The magnetic poles themselves are constantly shifting. The Earth's magnetic field is not fixed, but is constantly moving with the magnetic poles wandering over time. In fact, the north and south magnetic poles have been known to drift over the years, and the magnetic field itself is subject to occasional reversals, called geomagnetic reversals, where the magnetic poles flip. Though this reversal has happened many times throughout Earth's history, it doesn't happen suddenly, and it takes thousands of years for the poles to fully flip. So as we stand here on the surface of the planet, the magnetic field beneath our feet is quietly shifting and changing, shaping the environment in ways we can't even fully perceive. One of the most interesting aspects of the outer core is the role it plays in tectonic activity. As we saw in the mantle, heat and pressure drive the movement of tectonic plates, but it is the convection currents in the outer core that help set the stage for this activity. The molten metal of the outer core creates convection cells regions of hot rising material and cooler sinking material. This convection process, in turn, drives the mantle convection and ultimately contributes to the movement of the Earth's lithosphere. The entire system is interconnected, a delicate balance between heat pressure and material flow that results in the ever-changing surface of the planet. Perhaps one of the most mind-blowing features of the outer core is the fact that it's invisible to us, yet we are entirely dependent on its existence. The molten metal is hidden deep beneath the Earth's crust and mantle, but its influence extends far beyond its immediate location. The magnetic field it generates reaches across the globe, influencing everything from animal migration to modern technologies. Many animals, such as migratory birds and sea turtles, use the Earth's magnetic field for navigation. They can sense the field and use it to guide their movements even across vast distances. In fact, some researchers believe that certain species can detect shifts in the Earth's magnetic field with incredible precision. It's amazing to think that a process happening thousands of kilometers beneath the Earth's surface can influence creatures moving across oceans and continents. And if we're being honest, sometimes it feels like the core is one of the quietest parts of the Earth. Yet without the movements of its molten metals and the magnetic field it generates, the planet would be a much less hospitable place. The outer core is a true testament to the Earth's invisible forces quietly at work beneath the surface, keeping everything in balance. So as you lay back, imagine that deep down beneath your feet, there's a slow, unceasing churn of molten metals, creating the forces that drive the magnetic field and protect all life on Earth. The outer core is where the planet's invisible lifeblood circulates, and though we can't see it, its influence is felt in every compass needle, every aurora, and even in the very way we navigate our world. It's yet another reminder that the Earth is not just a place you stand on. It's a living, breathing organism that is constantly shifting, churning, and changing. Next time you feel the pull of a compass or notice the gentle swaying of the northern lights, you'll have a deeper appreciation for the quiet, molten dance happening thousands of kilometers below. At the very heart of the Earth lies its inner core, a place so deep and mysterious that it seems almost unfathomable to our senses. Here the pressures and temperatures are beyond what most people can even imagine. To put it in perspective, the temperature of the inner core is similar to the surface of the sun, reaching about 5,500 degrees Celsius, 932 degrees Celsius. The pressure is roughly 3.6 million times that of the atmosphere at sea level, enough to squeeze atoms themselves into denser forms. But despite these intense conditions, the inner core remains solid. It's a strange paradox. While the outer core is molten and fluid, the inner core is made of solid iron and nickel locked together in an intricate, dense structure. Why does the inner core remain solid when it's surrounded by molten materials? The answer lies in the balance between pressure and temperature. At these immense pressures, the iron and nickel atoms are so tightly packed together that they can't move freely. This means the material behaves like a solid, despite the fact that it would normally be a liquid at such high temperatures. This dense, solid core plays a crucial role in shaping the entire structure of the Earth, even if we can't directly observe it. The inner core is also incredibly dynamic. Though it's solid, it is still slowly growing. Over time, as the Earth cools, the material from the outer core solidifies and adds to the inner core. This process releases latent heat, which helps maintain the convection currents in the outer core and drives the geodynamo, the mechanism that generates the Earth's magnetic field. In a way, the inner core is the engine that powers the magnetic field, which we so often take for granted, but which is so vital to life on Earth. Imagine for a moment that the Earth's inner core is a kind of time capsule, a remnant of the planet's early days, and its story is written in the very metal that it's made from. This inner core has been cooling and evolving for billions of years, and with each passing moment, it shapes the way our planet functions. Its solid state is a crucial part of the Earth's ongoing evolution, providing stability for the layers above it and contributing to the constant movement of the outer core. But here's something fascinating: scientists have found that the inner core is actually rotating faster than the rest of the planet. The idea that the innermost part of the Earth might be moving at a different speed than the rest of the planet is both unsettling and intriguing. The inner core's rotation is thought to be slightly faster than the Earth's surface, and this has led to theories about how this affects the planet's magnetic field and even its day-night cycle. This differential rotation has sparked ongoing debates in the scientific community, with some suggesting that it could influence the generation of the Earth's magnetic field in subtle ways, possibly even contributing to occasional changes in the intensity of the field. The boundary between the inner core and the outer core, called the core mantle boundary, is also an area of significant scientific interest. This is where the Earth's magnetic field is generated, and where intense energy exchanges take place between the molten outer core and the solid inner core. These interactions are believed to help sustain the dynamo process, which is why the inner core's rotation could have an influence on the overall behavior of the Earth's magnetic field. The details are still being studied, but it's clear that this core mantle boundary is one of the most important yet least understood regions of the Earth. What does the existence of a solid inner core mean for the Earth as a whole? While it may seem like just one more layer of the Earth, its presence is a key reason why our planet is so geologically active. The movement of the solid inner core, combined with the convection currents in the outer core, helps drive the tectonic plates and sustain geological processes like earthquakes and volcanic eruptions. It also helps maintain the Earth's rotation and stabilizes its axis, which is why the seasons remain relatively predictable over millennia. But how does this influence our everyday lives? Well, everything from our climate to our weather patterns is tied in some way to the activity deep within the Earth. The Earth's rotation, which is influenced by the inner core, governs the planet's day-night cycle. This, in turn, affects everything from ocean currents to atmospheric circulation. The Coriolis effect, which causes winds and currents to rotate in certain directions based on the Earth's rotation, is a direct consequence of the movement of the planet, which is rooted in the dynamic interplay between the inner core and the rest of the Earth's structure. What if the Earth didn't have a solid inner core? Without it, the outer core would have no solid center to anchor its flow, and the geodynamo might not be able to operate in the same way. The magnetic field might collapse, leaving the planet vulnerable to solar winds and radiation. It's amazing to think that something so deeply buried beneath the surface can have such far-reaching consequences for the entire planet. As you rest your head, tonight, imagine this vast, dense ball of iron and nickel spinning at the center of the Earth, contributing to everything from the magnetic field to the rotation of the planet. The inner core is as much a part of you as the soil you stand on, even if it's a place you'll never visit. Its quiet, invisible work keeps the Earth moving and evolving, shaping the planet and all of us in ways we can't always perceive. So next time you think about the Earth, don't just imagine the land beneath your feet or the sky above your head. Think of the dynamic, complex dance of molten metals and solid masses far beneath the surface, creating the magnetic shield that protects us all. As you imagine the Earth's inner workings, consider the world of tectonic plates that float above the liquid mantle. These vast, slow-moving slabs of rock are constantly shifting, sometimes gently and other times with immense force. It's on their restless journey that we find the world's most dramatic geological events: earthquakes, volcanic eruptions, and the formation of mountain ranges. These plates are the Earth's outermost layer, floating like giant rafts on the surface of the mantle, with their movements powered by the heat and pressure below. Tectonic plates are made up of two distinct types: continental crust and oceanic crust. Continental crust is thicker, about 30 to 70 kilometers, 18 to 44 miles thick, while oceanic crust is thinner, at about 5 to 10 kilometers, 3 to 6 miles. The oceanic crust, being denser, sinks beneath the lighter, more buoyant continental crust in a process called subduction. It's at the subduction zones where some of the most intense geological activity occurs, leading to the formation of deep ocean trenches and the explosive eruptions of volcanoes. Have you ever wondered why some places seem to shake more than others? The movement of tectonic plates is responsible for creating the faults and fractures in the Earth's crust, which in turn cause earthquakes. In regions like the Ring of Fire, a horseshoe-shaped area around the Pacific Ocean, earthquakes and volcanic activity are frequent. This area is home to around 75% of the world's active volcanoes, making it a hotspot for tectonic activity. The energy released during these earthquakes is so immense that it can trigger tsunamis, shaking entire coastal regions and even triggering secondary disasters like landslides. But why do these plates move in the first place? It all boils down to the heat inside the Earth. As the radioactive decay of elements, like uranium and thorium, takes place deep in the mantle, it generates heat. This heat causes the material in the mantle to become less dense and rise, while cooler, denser material sinks. This creates a constant flow of material in the mantle, called mantle convection, which essentially pushes the tectonic plates around. In the grand scheme of things, the plates are moving at a snail's pace, only a few centimeters per year, but over millions of years, these slow shifts shape the continents, creating oceans and mountains in the process. As these tectonic plates interact with one another, they don't just move in isolation. They are constantly colliding, pulling apart, and sliding past each other. These interactions create boundaries that are categorized into three main types: divergent, convergent, and transform boundaries. At divergent boundaries, plates move away from each other, creating gaps where new material from the mantle rises to fill the space. This can lead to the formation of mid-ocean ridges, where new oceanic crust is created, or rift valleys where continents are slowly pulled apart, like the East African Rift. It's here where we witness the birth of new land masses, stretching and cracking as the Earth's surface slowly reshapes itself. Convergent boundaries are where plates crash into one another. One plate might be forced beneath the other, forming a subduction zone, which can lead to the creation of mountain ranges like the Himalayas. Here, the collision of India and Asia has created the world's highest peaks, a process that's still ongoing. At these boundaries, the immense pressure of the collision can also cause volcanic eruptions, as magma is forced upward toward the surface. The Andes Mountains in South America, formed by the subduction of the Nazca Plate beneath the South American Plate, are another example of how plate collisions shape the world. Then there are transform boundaries, where plates slide past each other, often causing earthquakes. The San Andreas Fault in California is a well-known example of a transform boundary. Here, the Pacific Plate and the North American Plate grind against each other, leading to frequent seismic activity. The shifting of these plates causes sudden movements in the Earth's crust, sometimes releasing energy that has built up over years, which can result in destructive earthquakes. As you lie there, maybe you're imagining these massive plates grinding against each other deep beneath your feet. Can you feel the slow, powerful rumble of the Earth as it moves, shaping the surface? It's not just the plates themselves that make this process fascinating. It's also the way these movements interact with other geological features. Think about volcanoes, for instance. These towering mountains of ash and molten rock are born from the Earth's restless interior. When tectonic plates collide or pull apart, they allow magma to escape, creating volcanic arcs, island chains like Japan or the Philippines, and even supervolcanoes that have the potential to alter the course of life on Earth. Some of these eruptions are so violent that they can reshape entire landscapes. The eruption of Mount St. Helens in 1980, for example, dramatically changed the surrounding landscape, destroying forests and creating new landforms. Yet it also brought about new ecosystems and a fascinating process of ecological recovery. The forces at play within the Earth's crust don't just destroy. They also give life to new landscapes, new ways for life to exist. The movement of tectonic plates also affects earthquakes, which are perhaps the most immediate dangerous consequence of this deep-seated activity. As stress builds up between two plates along a fault line, it eventually reaches a point where the pressure becomes too great to withstand, causing the ground to shake violently. In a matter of seconds, cities can be flattened and entire regions can be transformed. The 2011 earthquake in Japan, which was caused by the subduction of the Pacific Plate beneath the North American Plate, triggered a catastrophic tsunami and a nuclear disaster, illustrating the immense power stored within the Earth's crust. But while we often think of earthquakes as destructive forces, they also serve a purpose in the natural world. They help release the pressure that builds up between plates, preventing even greater disasters from occurring. Earthquakes can also create new landforms, such as mountain ranges, as tectonic forces push up the crust in dramatic folds. What's fascinating is that these processes, tectonic movement, earthquakes, volcanic eruptions, are all interconnected. They are part of a dynamic, ever-changing system that is continually reshaping the planet. And this process, slow and constant though it may be, is one of the primary drivers of the Earth's geological evolution. As you drift into a peaceful state, imagine the slow, constant dance of tectonic plates beneath your feet. The Earth is constantly changing, yet it does so in ways that are almost imperceptible to us. Perhaps tonight the quiet movements of these vast plates will remind you of the incredible forces shaping the world just below the surface. As you sink deeper into relaxation, imagine the deep mantle beneath the Earth's crust, a region where intense heat and pressure create a world that is both fascinating and unfathomable. The mantle, which extends from the base of the crust all the way down to about 2,900 kilometers, 1,800 miles, is home to the forces that drive the Earth's ever-changing landscape. While we focus most of our attention on the surface beneath our feet, lies an incredibly dynamic world where the slow, steady flow of material shapes everything above. The mantle isn't a solid block of rock as you might assume. It is more like a viscous fluid, a thick, semi-solid substance that behaves like a combination of solid rock and liquid. This may sound strange, but it's true. The mantle is made up of minerals that are solid at the Earth's surface but become soft and flow over time due to the immense heat and pressure. As you picture it, think of the mantle as a massive honey-like substance, flowing and moving at a pace so slow that it's imperceptible to the human eye. It's this slow, constant flow that drives the movement of tectonic plates and creates some of the most extraordinary geological events. The mantle is divided into two parts, the upper mantle and the lower mantle. The upper mantle, while still incredibly hot, is the part of the mantle that interacts most directly with the Earth's crust. This interaction is crucial because it is in the upper mantle that the phenomenon of mantle convection occurs. Mantle convection is a process where hot, buoyant material rises from the lower mantle, cools, and sinks back down, creating a continuous circulation of material beneath our feet. This slow, swirling motion is what fuels the movement of tectonic plates above, sending them drifting across the Earth's surface at a mere few centimeters per year. But why does this process matter? What does it mean for the Earth? And why is the mantle so important? The answer lies in the way that mantle convection works to create and renew the Earth's crust. As heat rises from the Earth's inner layers, it causes the material in the upper mantle to slowly move toward the surface. This upward movement can form features like hotspots, where magma from the mantle breaks through the crust, creating volcanic islands like Hawaii. As this magma rises to the surface, it cools, solidifies, and becomes part of the crust, slowly renewing the Earth's surface. Imagine for a moment how this dynamic system beneath your feet might feel. The pressure building the material, shifting, creating subtle tremors deep down. It's a rhythm that is invisible to us, but essential to maintaining life on Earth. Without this ongoing movement, the Earth's surface would be static and lifeless, incapable of supporting the ecosystems we rely on. It's a reminder that beneath every moment of calm, the world is teeming with invisible activity, a dance of forces that we can't see but are always working to support life. It's not just volcanic islands and hotspots that are created by the mantle's movements. In fact, the mantle plays a critical role in the formation of mountain ranges. When two tectonic plates collide, the mantle pushes up the crust, folding it into towering peaks. The Himalayas, for example, are still rising today as the Indian plate pushes into the Eurasian plate, a process that has been ongoing for millions of years. Every time you look at a mountain, remember it's not just rock and earth. It's a product of a vast, complex system operating miles beneath the Earth's surface. The mantle also holds the key to understanding earthquakes. While the majority of seismic activity occurs at the Earth's crust, it's the forces originating deep within the mantle that set the stage for these dramatic events. As plates are pushed and pulled, the stress that builds up in the crust can cause it to snap, sending shock waves through the Earth. The motion of the mantle creates the environment in which these faults exist, and when the pressure becomes too much, it triggers the release of that energy. Perhaps the most mind-boggling aspect of the mantle is the way it is linked to the Earth's core, a place so deep and inaccessible that we can only guess at its true nature. The core is divided into two parts, the outer core and the inner core. The outer core is composed of liquid iron and nickel, while the inner core is solid and made of similar materials. The outer core is responsible for generating the Earth's magnetic field thanks to the geodynamo process, where the movement of molten metal creates electric currents. This magnetic field is essential for life on Earth, protecting us from harmful solar radiation and helping guide animals on migrations. The movement within the outer core helps maintain the dynamo, and as a result, we live in a stable magnetic environment that shields us from the harshest aspects of space. Understanding the mantle's interaction with the core and the crust helps explain why the Earth is such a dynamic and ever-changing planet. Beneath your feet, the mantle continues to flow, shaping the surface and creating the conditions for life. It's this constant motion, from the hot, dense material at the core to the crust we stand on, that makes Earth unique in our solar system. As you think about these deep, subterranean processes, imagine the incredible forces beneath you. Forces that are shaping the world with each passing moment, slowly, almost imperceptibly. The Earth's mantle reminds us that the world is always in motion, even when it feels still. And just as you drift deeper into rest, the planet itself is also shifting with the same kind of quiet determination that allows mountains to rise and valleys to deepen. As you approach the final stretch of this deep dive beneath the Earth's surface, it's time to think about the core, the most mysterious and fascinating part of the planet, hidden so deep that it remains out of reach for even the most advanced technology. Imagine for a moment lying here under the gentle weight of Earth itself as the core hums quietly in the dark. This isn't just any hum, it's the heartbeat of the planet, the driving force behind everything you experience on the surface. We often think of the Earth's core as something static, something unchanging and immovable. But in reality, it's an incredibly dynamic system. At the center of the Earth, about 6,400 kilometers, 3,980 miles beneath your feet, lies the inner core, a solid ball made primarily of iron and nickel. Surrounding it is the outer core, a fluid layer of molten metal that behaves like a magnetic dynamo, constantly generating the Earth's magnetic field. This magnetic field is something you might never think about until you do. It's the invisible shield that protects us from the sun's harmful radiation, guiding compasses, and ensuring that migratory animals don't get lost during their journeys. And it's the steady rhythm of the Earth's pulse that sustains our world in ways we cannot always perceive. Let's think about the outer core for a moment. It's a wild, active zone, liquid iron and nickel swirling and churning at incredibly high temperatures between 4,000 degrees C and 5,000 degrees C, 200 degrees F to 9,000 degrees F. As you rest, imagine the fluid metal endlessly moving, constantly shifting beneath your feet. Its motion is the reason for the magnetic field that surrounds Earth. The heat from the inner core causes the molten metal of the outer core to move, setting up convection currents. These currents create electric currents, which in turn generate the magnetic field we depend on for our protection. This process is called the geodynamo. You might be wondering, how does this all tie into our everyday lives? The magnetic field generated by the core not only protects us from dangerous solar radiation, but it also plays a huge role in technological navigation. Our compasses, for example, are guided by the magnetic poles, which, by the way, aren't fixed. They actually wander over time. The magnetic field shifts and the poles drift slowly across the Earth. If the magnetic field were to disappear, our world would look a lot different. Without the magnetic shield, our atmosphere could be stripped away by solar winds, leaving the Earth exposed to cosmic radiation. The inner core, while solid, is under immense pressure, more than 3.6 million times the pressure at sea level. At these pressures, metals don't behave as you'd expect. They're solid, but they're also moving and vibrating, albeit in a manner that is incredibly slow. This slow, constant movement creates a vibration that echoes through the Earth. It's almost like a heartbeat, a pulse that's subtle but steady, rippling through the layers of the Earth. Some scientists believe the inner core even grows over time. As it cools, solid iron crystals form, and they settle toward the center, adding to the mass of the core. This process is part of what keeps the Earth warm, and more importantly, helps maintain the dynamo effect that generates the magnetic field. But how do we know all this? How can we understand a world so far beyond our reach? The answer lies in seismic waves. These waves, caused by earthquakes and explosions, travel through the Earth and help us see what's inside. Different seismic waves move at different speeds through solid, liquid, and gas. By studying how these waves travel, scientists can infer the composition of the Earth's interior from the crust all the way to the core. It's like listening for echoes in a cave. The sound of the waves tells us how the rock, magma, and metals are arranged and how they behave under stress. Now pause for a moment and ask yourself, how could something as massive as the Earth's core possibly affect the way we live? The core not only affects Earth's magnetic field, but also its temperature regulation. The heat from the core helps drive volcanic activity, which in turn influences weather patterns and can even shape the continents. Without the heat from the core, Earth would likely be a much colder and less hospitable place, unable to support life as we know it. Interestingly, the magnetic field isn't the only thing the core influences. The internal heat helps to drive the movement of the Earth's crust, and in turn, the crust's movement causes earthquakes, volcanic eruptions, and mountain formation. It's all interconnected. The core's movements are the silent instigators of the Earth's restless surface. Beneath the crust, the inner workings of the core influence plate tectonics, a process that has created, destroyed, and reshaped the continents over millions of years. You might also wonder if the core will always remain the same. Is it forever stable, or will it change over time? The truth is, the Earth's core is still evolving, and it's likely that its processes will continue to shape the planet for billions of years to come. Some scientists believe that one day the inner core will solidify completely, while others think that it could eventually melt into the surrounding outer core. Either way, it's a slow process, so slow that it is barely noticeable in the timescale of human life. Before we close this journey, think about the sheer scale of what we've discussed. The layers of the Earth, from the crust beneath our feet to the molten heart of the core, each part playing a role in sustaining life, weather, and the very shape of the planet. Beneath you there are forces too vast to comprehend, pushing, pulling, and shaping the world over time. As you rest, remember that these unseen forces continue to shape the planet, even as you drift into a peaceful sleep. The Earth's pulse goes on steady and relentless, its heat, pressure, and movement creating the world as you know it. And just as you've learned more about what's beneath your feet, let yourself rest in the comforting knowledge that the Earth itself is always at work, quietly supporting life and keeping you safe. Sweet dreams.